ఇది సివిడిబి మెంబర్ అతను
సార్ దాస్ కుమార్ ఎవరు దాస్ అని అంటున్నా రాజేష్ కుమార్ దాస్
చాలా ఎస్టిమేట్ గా పెట్టాడు. కొద్దిగా చూసుకోండి.
రాలే ఎవరు ఇంకా
ఆన్ చేస్తున్నారు. కాదు ఇది ఆన్ అయిందా? లింక్ రావట్లేదు ఎవరికి?
వచ్చింది కదా, ఏదే ఇదే కదా లింక్
వర్కింగ్
ఇదే కదా 28 4 గంటలకు
వస్తుంది కదా సార్.
అదే సార్ లైన్ వచ్చింది.
6 మెంబర్స్ చేయండి.
ఇప్పుడు వచ్చింది
7 మెంబర్స్. వెంకట సుబ్బయ్య గారు, మామిడాల సో అందరికి
వచ్చారా సెక్రటరీ? ఇక్కడ సరే మరి ఎలా
ఎవరు సెక్రటరీ ఎలక్ట్ కూడా ఇన్వైట్ చైర్మన్ He is getting blind into it. Yeah.
Last time. Respected members. Respected Chairman of IUIP, Council Member Dr. A.S.N. Raju and Chairman elect Professor Dr. Ramana Bhanatu, and our Joint Honorary Secretary Dr. D. Rama Madam, and the Senior Committee Member Professor Mainuddin, and Class Committee Member T. Venkateswara Garu. I welcome you all this evening for Engineer ATLURI Venkateswara Rao 18th Endowment Lecture on the topic Design of Cost-Effective Control Strategies for High Quality Power to AC Microgrids. This is the topic. So now hand over the floor to. So I also congratulate Professor Dr. P. Satish Kumar Garu, committee member, who is also convener of this event. So I invite all the members in the Zoom also. Now I hand over the floor to the chairman.
Thank you, sir. Mari Ramesh Garu, Honorary Secretary elect. Now, before starting the program, I request the dignitaries present here to first garland the portrait of ATLURI Venkateswara Rao Garu. Sir, all of you can.
ఇక్కడ ఫ్యాన్ ఉంది, కొద్ది జాగ్రత్త తీసుకు. ఎవరన్నా వేస్తే వాళ్ళ
వీడియో చూపిస్తాను. వీడియో పెట్టుకోండి మీరు. అక్కడ ఉండు, అది ఇచ్చేసాడు.
స్లైడ్ వస్తుంది. ఓకే, ఇప్పుడు కరెక్ట్.
చేస్తున్నాను సార్.
గుడ్ ఈవినింగ్ విజయప్రసాద్ గారు.
గుడ్ ఈవినింగ్ సార్, బాగున్నారా?
Respected keynote speaker, Dr. Mamidal Vijay Karthik, Associate Professor cum Training and Placement Officer, CMR Engineering College.
Very good evening, sir.
Dr. Amit Nayak,
మైక్ చూడండి ఫస్ట్.
Admin Elect IA Telangana State Center. Engineer Bali Ramesh, Honorary Secretary Elect IA Telangana State Center. Dr. Ramesh, Council Member. Professor Dr. Muhammad Moinuddin, Committee Member. Engineer Shafiq Garu, Ismail Garu. Engineer Tanir Venkateswara Garu, past Committee Member of IA Telangana State Center. Dr. Rama, Joint Honorary Secretary IA Telangana State Center. Engineer Vijay Prasad, Professor Raman Ramarao Garu, and all the participants and sir, convener, importantly, the convener, Professor Dr. P. Satish Kumar Garu, FIG Committee Member, IA Telangana State Center, all the invitees, ladies and gentlemen, good evening to all of you. Today I feel it is a great privilege and honor to be amidst this August gathering and extend a warm and hearty welcome to the keynote speaker and all of you to Engineer ATLURI VENKATESWARA RAO 18th Endowment Lecture. Today I am very happy to be associated with this memorable event. I am glad to inform that the Telangana State Center of the Institution of Engineers, India has been regularly organizing endowment lectures which are totaling to 20 in a year in the honor of eminent engineers like Engineer V. Subbarao, Engineer M. Tirupati Reddy, Professor K. Gopichand, Dr. J. Purushottam, Engineer G. Prabhakar, Engineer Koka Krishnamohan Rao, Engineer Balakrishna Reddy, Engineer G.V. Subbarao, Engineer T. Hanumantarao, Engineer A.P. Ranganath Swami, Dr. S. Raghavachari, Dr. Narla Tatarao, Engineer Matul Gopalrao, Engineer Viram Kodreddy, Engineer R.L. Rasu, Engineer ATLURI Venkateswara, whose endowment lecture today we are organizing, Dr. Jan A. Murre, Dr. N.V.R.L.N. Rao, Engineer Sel Venkatkrishna Iyer, K.V. Srinivasa Rao, and M.L. Swami, Dr. A. Ramakrishna, and I. Basavarazu lecturers. I am glad to brief about Engineer ATLURI Venkateswara Rao, former Chief Engineer APSCB and Chairman Alvin Limited. Engineer ATLURI Venkateswara Rao has contributed significantly for the overall development of the state of Andhra Pradesh, and his contributions to the field of electricity and HRD as laudable and memorable. Engineer ATLURI Venkateswara Rao served the Andhra Pradesh State Electricity Board for more than 3.5 decades in various capacities and retired as Director Personnel. To his credit, for ATLURI Venkateswara Rao brought out more than 40 publications in the areas of engineering, HRD, stress management, and personal management, etc. In addition to publication of several of his articles in leading newspapers in India, Engineer Rao was born on September 28, 1927. In pursuance of the resolution of the then erstwhile AP State Center, so far 18th endowment lectures are organized since 2002 in memory of great engineer ATLURI Venkateswara Rao and delivered lectures by persons of high eminence. Today, Telangana State Center arranged Engineer ATLURI Venkateswara Rao 18th endowment lecture on the topic Design of cost-effective control strategies for high-quality power to AC microgrids. Since you are anxiously waiting to hear the talk from our eminent speaker, I am limiting myself and hope that you will really enjoy the talk. So on behalf of the Telangana State Center of IEA and on my own behalf, I once again extend a hearty welcome to keynote speaker Dr. Mahamudala Vijay Karthik, Associate Professor, Training and Placement Officer, CMR Engineering College, and all of you to this important endowment lecture. Thank you, one and all.
ఇది బంద్ కావాలంటే
Now I request Professor Dr. Satish Kumar, convener of the event, to introduce the keynote speaker, Dr. Mahamudala Vijay Karthik.
లీవ్ సారీ
లీవ్ మనకి అవసరం కదా ఇంకో చేయను
Sir Satish garu.
అది మైక్ చూసి చూసుకున్నారా మైక్ అది ఇంపార్టెంట్ చాలా ఇంపార్టెంట్ మైక్ చూసి
Sir join అయినట్లేరు. Sir Satish garu. No. Ratan garu. Ratan garu బయోడేటా ఉన్నాయని పిలిచారు. Sir, 1 minute, please. Sir Vijay Karthik garu.
Sir, very good evening, sir.
Sir, can I have your biodata, sir, to introduce you? Any soft copy is there, sir?
Yeah, I do have it, sir.
Sir, it is with us, sir.
Okay, sir. Okay, sir.
Sir, now I request Professor Dr. Mohammad Moinuddin garu to introduce our keynote speaker, Dr. Mahamudala Vijay Karthik.
Very good evening, Professor and Dr. Introduce today's keynote speaker, Indian professor, Dr. Mangalara working as a lecturer in electrical and electronics engineering, who are training and placement officer at the CMA College of Engineering, Hyderabad. He has a 70 years of teaching experience, including a research experience in the field of power quality, smart grid, microgrid, and renewable energy sources, electric vehicles. He received his PhD from a medical engineering marketing, a Greater Nevada. Living from the Laboratory Institute of Technology, Usmania, Hyderabad. He is a reviewer for a featured photojournalist, Springer Electric Systems, Springer artificial intelligence, etc. His area of interest is about power systems, smart grid, microgrid, power quality, artificial intelligence, electric vehicles, and grid interaction. He has 15 patents and 4 undergrad of 2 patents granted by ITL 7 published patents. 2 years of patents. He published more than 40 international and national journals, conference, including a SCI and Doctor's Focus, IEEE. He received INR 60 as research consulting fund, funding from AICT, MSME, IIMEO, etc. For example, Bob was he delivered more than 60 seminars, lectures, he published a book chapters in a world meeting, one book chapter in a Taylor he has authored 3 textbooks. He won a British award for 3 years at the CMRC and a best teaching placement officer award at the national level. So thank you so much for having me. Great today for sharing your knowledge for our audience and providing it. Thank you, sir. So please over to chairman for introduction. Thank you, sir.
Thank you, sir. Professor Dr. Mohinuddin Garu for the nice introduction of our keynote speaker. Now I request our keynote speaker, Dr. Mamdala Vijay Karthik Garu, to deliver endowment lecture.
Thank you, sir. Thanks for the introduction. Myself, Dr. Mamdala Vijay Karthik, I'm working at Associate Professor at CMR Engineering College. It's really a pleasure and honor for me to deliver this lecture for the one of the greatest personality in the field of electrical engineering, sir. With your kind permission, I would like to share my screen, sir, for the presentation.
Okay. Share చేస్తున్నారా?
Yes, sir. Yes.
Sir, is my screen visible, sir?
Yes, sir.
And my voice and screen, everything is okay, sir?
Okay, sir. Okay.
Yeah. So today on occasion of ATLURI VENKATESWARA sir, uh, Institute of Engineers have organized an endowment lecture, and I'll be presenting the lecture on the topic design of cost-effective control strategies for high-quality power to AC microgrids. The reason why this topic is very important nowadays is from the world is completely changing from traditional electrical power system to this modern power system, which includes smart grids, microgrids, etc. So in this area, there are certain problems which need to be addressed, and a lot of research work is going on in this area. So one of the major area is that this supply of the high quality power for these microgrids. My complete presentation outline is first introduction, motivation, what exactly the problem statement I'm taking a case study to explain this. I'm taking a case study and will be explaining about this. Next, about what exactly the objectives will be, what exactly the literature was all about, and what the control algorithms have been implemented recently. And based out of that case study, what the results and discussion, what exactly the future scope will be. So speaking about this, what exactly microgrids, everything is, why this technology has come into picture. This technology, smart grids and microgrids has come into picture since last only 25 years. Before 2000, no one knows about smart grids or microgrids. It's only about traditional power systems. We used to have generation, next up to distribution, and up to utilization. But right now it is something like local generation, local transmission, local distribution, and local utilization. That is nothing but our smart grids and microgrids. Recently we have seen that due to many reasons, weather conditions, natural disasters, there is a complete blackout of power in India as well as across the world. So based out of those things, the research has been started with respect to these microgrids and smart grids. We can see that whenever there is a power of in airlines and at hospitals, the distributed generators will be used to where local generation of power and distribution happens. So this is the major point to understand about this technology. Nothing but local generation and local utilization, simply taking out about the transmission. So microgrid is nothing but it is integration of all the distributed energy resources. What are all that distributed energy resources? Are nothing but the batteries in our vehicles act as a distributed energy resources. As one example I have given. So it is nothing but in simple, operating in islanding mode and providing the best reliability for our grid disturbances. Even at local power stations, where what we have in our areas sometimes face lot of disturbances. To avoid the disturbances, to avoid the major power losses, and to keep the continuous power supply, this microgrid is into consideration and is very much into development in next to 50 years, most probably 25 to 50 years. In that range of time, we can expect all the houses in our country to have this system. Already central government of India is working on this, and a lot of IITs and NITs are also professors. This research work is carried on in a great way. And one of the challenges in this technology is to have that electronically coupled distributed energy sources balancing. The control and the balancing of electronically coupled distributed energy resources is one of the major challenges in this microgrids. And lot of research is being going on with respect to this, and the major objective about this session, what I'm going to have is about how to control different strategies, how to balance the energy, how to provide the acceptable IEEE standards, acceptable power quality, and how to have the continuity of the operational modes, transition on and off mode. Yeah, these how the session will be going on, and it's not that easy. In simple, if we speak about any local simulation kind of thing, it may be easy, but practically speaking, it is very sensitive, and we need to ensure that every parameter in the system is being maintained at the desirable rate. And of course, power quality issue in microgrids compared to the traditional distribution system is a challenging one because of very low inertia and short circuit level, which is because of the local generation and distribution. And this is what the typically complete microgrid connection is. We can see with a lot of resources, energy storage, battery, we take some capacitors, we take some local generation, and we can have a control unit where you can have a distributed energy system. This is where our complete work will be discussion happens. The discussion of the work will be happening over here. Whenever electronic items, electronic devices are infused in electrical system, we get some disturbances with respect to current, voltage, and power that are classified as power quality problems. Why not the major disturbances? Means these are of very low level disturbances. That's the reason why we call it as a power quality problem, different from faults of the electrical systems. So these are typical microgrid in grid connected mode. For that, what exactly for the basic understanding, we have different power devices like DC to AC, AC to AC, bidirectional DC AC, and different kinds of power systems interfacings will be there. So for everyone's clear understanding, we will have a common AC bus. We'll be having a common AC bus, and a microgrid control center will be there, which will be connected to the main substation, which is in our areas, and also connecting with the local supplies. We can have solar power generation, wind power generation, the batteries, our household, all electrical and electronic appliances also will be part of this microgrid. Of course, electric vehicles as well. In simple, for everyone's understanding, just to say that microgrid is nothing but, in usual or normal mode, we'll be getting the power supply from the substation or the utility grid. And whenever there is a discontinuity in the power supply from the main grid, we will use these appliances, maybe solar power, wind power, battery, etc., electric vehicles, batteries. These things will be taking into consideration to make sure the continuity in the power is available in that particular area. So we have again in this microgrid different topologies based on the different networks and different controlling things. Centralized power, where all the microgrids will be connected together, and happens happening will be like something, wherever power will go, any microgrid can be able to supply the alternate power. Distributed control, it is nothing but only up to that local grid. And decentralized one, this is what the major point is, that only a simple physical connection will be there, and we'll be having local devices to supply for the to supply the alternative power for the microgrid. Next, we can see like what's the difference between the centralized control and distributed control. There are many things we can see that distributed control is having lot of advantages compared to centralized control. Maybe operating cost, even the devices cost, which is very robust, and construction of these devices also may be easy in distributed control. Reliability, communication, complexity reduces, all these things will be happening. And apart from that, flexibility, even on with respect to design and implementation also, we can see complex algorithms may be required for centralized control, whereas simple control algorithms are required for distributed control. And hardware controlling also we can use with respect to centralized control. Powerful computer is required, whereas with respect to economic point of view, embedded controller is enough for distributed control. Time scales implementation also very easy in distributed control compared to the centralized control of the microgrids. So these are the controlling stages of the microgrid with respect to time. So whenever you can see a main grid is there, we will have the switching device over and microgrid, which will be connected to different devices. We initially, whenever there is a problem, primarily control, we need to focus on the voltage stability, power quality, frequency stability, and power sharing. All happens between 0.2 seconds to 1 seconds. And secondary control will be with respect to voltage restoration, frequency restoration, power sharing improvements. This controlling happens between 2 to 10 seconds. And the final one is tertiary control, which happens for about economic dispatch, energy management, and congestion management. Usually happens between 20 seconds to 300 seconds. So we here are focusing on the primary control things. If this primary control is maintained in a most optimized way, then definitely the next secondary control and territory control, getting the things into normal condition, time reduces. In electricity, even a 0.1 second of delay in things also makes major loss in crores to the electricity system. So we are focusing here that system is getting into normal as soon as possible. Fast response is what is expected from this. This is just a case study I'm taking about three electronically distributed energy resources, electronically coupled distributed energy resources, where you can see utility grid is there, and we are having it is distributed into three different areas, which we are calling it as ECDER1, ECDR2, ECDRT. Load is also connected. This is about the single line diagram. And if we speak about if we design it into practical way, we can see what exactly the research is going on is here. What best design in a simplest way, reducing the complexity of the system can be happening over here. So, and how best, yeah, how fast we can have the normalcy of the working of these grid connected activities. So for that, we are using here smart impedance converter as well as smart impedance. Once this smart impedance converter will be at one place, which will be communicating with the grid side and the microgrid side, whereas this smart impedance system will be communicating with the load side. So again, these two will be in communication to ensure that whatever wherever there is a power quality problem, these two together communicate in the smart way and get back the system into normalcy. So usually what major power quality issues happen where these electronically coupled distributed energy resources are placed, harmonic load sharing. Whenever there is a load disturbances, harmonics will be happening, fluctuations, resonance problem will be happening due to series and parallel impedances, which may be consisting of inductors and capacitors. And of course, from islanding operation to grid connected mode, that is load, onload to offload and offload to onload, flickering, current and voltage levels changing from SPACs to swells and up to normalcy, and transients as well, voltage and current tranches, and more importantly, the line due to the line resistances greater the having the greater value during this disturbances or power quality issues greater than the line reactances. So we need to ensure that all these things are into consideration when we are addressing or designing an algorithm to ensure the power quality problems are in check. And what effect due to that power quality problems, what will be the effect? Economic feasibility, extra hardware is required, separate controller will be required, we will be having a degradation of quality in voltage and power. Of course, network losses will be there, slowdown of the operation. We can see that there is a fluctuations during uh, rainy season or some peak summer season in the electricity voltage and power. So all this happens because of this power quality issues. And of course, switching frequency fluctuations, all these things, if we are considering together, we need to have extra hardware to control them. And coefficient values will also be required for any electronically coupled distributed energy resources. To have the synchronization, that coefficients should be in the IEEE standards level. If we are not maintaining that, then the system will collapse. Of course, the voltage, current, magnitude levels as well, and the duration. If there is a transience in the voltage and current magnitude levels, and if we keep them continuing for more than limited permissible time, the entire system will be collapsed. And of course, the quality of the system is important. Non-linear loads and droop control will not work properly for this ECDERs during the load sharing between them. These are the major effects which is happening if we do not address the power quality issues in the given time. And what exactly why this is taken into consideration is very simple, like microgrid, as said, what exactly the motivation, what exactly the motivation behind this is. As said, this is the fastest to growing technology in the field of electrical engineering, and we required coordination between the loads and the micro generation in this distribution system. Of course, local control, this is very very important point. As said, in the next 25 years, power generation and utilization, eliminating the transmission and distribution will be happening at your house only. That is the local control, distribution control, what we call. And in case of any kind of disturbances, we need to ensure that without major effect to the microgrids, we need to isolate it, and again ensure that the continuity of the supply should also be there. And advantages, definitely the design for the local needs changes from place to place, and we need to ensure wherever at whatever the place or whatever the state, place, country, we need to ensure uninterrupted power supply and local reliability and without any losses. So with all this flexibility, we can say that microgrid concept is one of the evolving concept, and power quality issues in that practically need to be solved. If we are not solving these issues in its preliminary stages, going ahead, microgrid concept technology may not be feasible. So to make sure the cost of all this electricity generation and utilization comes into a economic feasible economic zone, we need to answer all these problems with respect to power quality. And what exactly the this research is going on presently? I'm working on this research work since last 5 to 6 years, and been done a very good implementations and being presently used at Chennai as well. Chennai, one of the universities where this power microgrid is into place physically. And what exactly we are working on this is we are developing different algorithms and to ensure that mitigating all these power quality problems, whatever have been mentioned, and in the acceptable accuracy level, we need to ensure this microgrid is operating. And this algorithms, whatever will be implementing, maybe from conventional algorithms like genetic algorithm, artificial intelligence, up to artificial intelligence, we are ensuring that whatever the microgrid possibility to eradicate or to mitigate the power quality issues should be time effective and cost effective to reduce the burden of additional equipment in the power system. So basic objective as said, we need to develop, simulate and study about this cost-effective microgrid control and making sure that effects of power quality issues like harmonic load sharing, resonance problem, transition from the islanding operation to grid connected, voltage and power, current quality, sparks and spells, transients, all these things we will be focusing and making sure the algorithm answers all these problems. And depending on these above objectives, we will be designing it and different hybrid algorithms which will be suitable for that particular microgrid. We will be ensuring that to design and improve the power quality levels. We have already carried out a lot of MATLAB and simulation works. These were practically done in connection with the physical equipment. And as said, this present work is being carried out since last 6 years. So since last 6 years, it's continuous improvements are also seen, and we have published one patent, and of course, one patent is also granted upon this. Uh, and going ahead, a lot of literature work has happened over. A lot of literature work since, as I said, since last 25 years only. This microgrid and smart grids technology has come into picture. We can see a lot of people have work on this literature things. I'll just come to the conclusions of this uh, literature. Different methods were used to ensure the power quality issues have been addressed. Like PI control has been used in reference frame and national reference frame and synchronous reference frame. Proportional resonant controller, hysteresis current controller. We can see that there are advantages as well as disadvantages of the methods or the algorithms what been used. And again, coming till the neural fuzzy control methods and up to neural networks also, we can see different methods have been used. If we see the latest one like fuzzy control and neural networks based, we are seeing that some advantages as there, uh, disadvantages are also there, like slow control method and lack of performance in offline training methods. So to overcome all these disadvantages, we have been working on different algorithms, and which I will be discussing 2 3 algorithms where we have seen a lot of improvements. So whenever I have taken a asset, I have taken the microgrid with some configuration, electronically coupled distributed energy resources, where we are operating. 3 ECDRs we have taken, and you can see the microgrid parameters what we have taken for the grid voltage side and inductance resistance values. For one of the ECDR1, ECDR2, we have taken different parameters, resistance, inductance, and other parameters, capacitance as well. For ECDR3, these are all the parameters which we have used in this case study, what we have taken. Smart impedance, this is what the additional, previously whatever the literature has been we have seen, none of them have used any smart impedance. They have used controllers. Single controller has been used to control at utility grid side, microgrid side, and ECDRs. But as shown previously, I have taken the smart impedance to control separately the ECDRs at the utilization side and at the uh, production side, generation side, another smart impedance. So these are the parameters for that, for different ECDRs. Initially, this was the first major development we have done. This model predictive control algorithm was used in this power quality improvement, where prediction of the microgrid time has been done. Next to optimization part has been done, and by using the control rule, we have made sure the correction part is done. And if constraints are in our limitation, it is fine, and we'll go to the next iteration. So even cost effective, as said, cost effective is also very important. Bringing on a lot of hardware definitely is not recommended in this system, which usually goes into crores. To reduce that cost also, we have made sure that MPC, normal MPC, is modified, and this cost effective function is also included in that model predictive control by taking transition modes weight factor as well. So we can see different, as I have said, 3 different ECDRs have been taken. We'll be having 8 states from 000 to 111. Different switching states will be there. So based on those switching state, we have even defining the cost function for this model predictive control as well. So initially for 000, we'll start off the simulation process, and we'll carry out till the level of 111 state, switching state. So whichever the switching states is giving the optimized cost function as well as the optimized power quality performance, we'll take that into consideration. Is what the simulation system is all about. We have taken the non-linear load, and 3 ECDRs has been connected. We have different modes. Connection has been there. Smart impedance converter system design. This picture speaks about different impedance, smart impedance design for the each and every ECDR. Is all about total MPC control of what we can do. This was a simulation which was carried out. These results have been for model predictive control based on ECDR1 and ECDR2. These are the current waveforms. We can see there is a disturbance, and coming to smart impedance based load currents, we can see the levels of the current at different ECDRs. These all about from standalone operation to islanding operation and output of the second ECDR1 and first, second, and third ECDR. We can see how the fluctuations in the current is happening due to power quality issues. There is no normalcy. So this is where we need to focus on. And you can see summation of before all the waveforms. I can simply say that you can see TST value is 26.07%, which is very, very high value. In this model predictive control using the smart impedance, we have seen that 26.07% is the total harmonic distortion value, which is very high. And to enhance this, to enhance the performance, we are predicting some hybrid models. Same for that, instead of model predictive control algorithm, we are proposing ANN, artificial neural networks, and genetic algorithm based. So what here is artificial neural networks here will take care about the communication with respect to electronically coupled DERs, whereas genetic algorithm will make sure it will give the proper switching functions to the utility side. So again, these two AN and GNN integrated complete control strategy will be communicating with each other to provide the proper switching at any kind of power quality issue, maybe harmonic expansions, whatever happens, making sure to have the better control compared to the previous one. So optimization is also important. So as said, this was replacing the model predictive control system with ANN and GA controller, separate controllers being used for ECDRs and microgrid side. So this was the cost function. We have taken the real part and the imaginary part where optimization of the cost function, ANN is predicting the cost function, and ECDR inverter is being controlled using the ANN. This is the layer for that, where we are giving the previous outputs as the inputs. Hidden layers will be working on the whatever the best possibility is there, and the output will be optimized. Output will be given to the inverter and the ECDRs. As said, we are using the shallow ANN model over here, and the principle is layered perception in order to work properly. This is very important. And hidden layers very low number of hidden layers have been used so that the controlling approach is proper with less amount of memory. That is nothing but reducing the complexity in the system. And number of variables are also will be reduced when hidden layers are also reduced. And the use of ANN training results definitely affects the cost as well. Compared to previous model predictive control system, this ANN makes sure that the cost is reduced compared to previous one. And smart impedance controlling through genetic algorithm, you can see that algorithm parameters has been given over here. They will calculate the initial weights and will give that initial weights for the simulation model. They will again go for the evaluation. Next, if this evaluation is better than the previous one and it is maximum optimized way, then that is the optimal result. Or else again it will go to some next set of value selection, crossover, mutation happens, and the again next level of population will be calculated. Is what the simulation model of ANN and GA. These are the results what been expected. Just I'll go. You can see here total harmonic distortion previous for the previous method was 26 point change percentage. We can see here by using this method it is 18.32 percentage. So still we can improve a lot to ensure that still more improvement is happening for this TSD. We have gone for ANFIS PSO algorithm, where ANFIS is replaced, ANN was replaced by ANFIS, and Gentic algorithm was replaced by CRPSO algorithm. And cost function also, same cost function we have kept, so that best comparison happens between the algorithms and we can get the optimized value for the cost as well. You can see that we have went for adaptive neural network. As and when the changes happens on the spot, it adapts and takes up on the practical values which is coming, and hidden layers will make sure the best combination and give us the best effective value. This is what the neuro fuzzy infusion and controlling. It was not only ANN, but it is neuro as well as fuzzification is also happening, different membership functions. And we can see that this technology is built to make sure the reduced value of the FST and TSD compared to the previous one. And back plant propagation was the algorithm which is used in this ANFIS controller. And as said, Gentic algorithm was replaced by craziness based particle swarm optimization technique. So the grid parameters will be given and the system will be set up, and the logistic chaos method is used to initialize the particle swarm initial one. And again normalization and the optimization, configuration, calculation, evaluation will be happening. And adaptive value, whichever is the best adaptive value, will be taken care. Next, individual SWAM will be refreshed and compared to the previous one. And next to fresh velocity and location will also be calculated. So this algorithm is such that automatically it will optimize to whichever the optimized value is there, it will locate that place. And we are ensuring that the proper calculation is happening with respect to the velocity as well as the location of that particular swarm, which is nothing but the optimized solution, which will give it to the fuzzy neuro point and ensures the TSD value is reduced. Different formulas and what the population size we have taken and what is the maximum iterations we have done and what is the from this practical value we got the craziness value, best value is 0.2. They are picked from different states, different combinations have been used, and different things. Just getting into the results, we can see the total harmonic distortions have come down from 18.32 to 6.53, which is a really drastic reduction. But even the 6.53 percentage of total harmonic distortion is really high. So we will be working out to reduce much more. So recently came a gray wolf optimized algorithm in combination with the artificial intelligence, which is really yielding a great result. We have used that gray wolf optimization algorithm where same controller. Even previously, we have seen two different controllers were used at grid side and at ECDER side. Now, this gray wolf algorithm, optimized algorithm, will be making sure same algorithm and same control strategy is used at both the sides, which again reduces the cost of the entire system. So we have taken the cost function of this gray wolf optimized algorithm, making sure the here CEGWO represents the control function. We have the output power, we have smart impedance power output as well, and the transfer function also. Plus, the fitness function is also taken into consideration. We have seen a different cost function altogether. Taking practically the values of the TSD and FSD here, which ensures the fast recovery of the system from these power quality problems as well as the cost. Economically, cost will also be affected. So this is how the power controlling operation happens in this gray wolf algorithm. We can see that usually unbalanced power controlling coefficients are taken. The coefficients, the values are taken, and the parameters will be initialized from the gray wolf algorithm. Best generation and selection positions will be taken about alpha, beta, and delta values. Whatever the best fitness function values fits, that need calculation will be done. Updating of that alpha, beta, and delta value for the maximum fitness in the each ECDERs. If update the positions are updated, yes, positions are updated, discreting the positions, re-ranking the every index value based on their weights, calculating their fitness function, again updating the value of alpha, beta, and delta. And if everything is fine, okay, maximum optimized value we have gained compared to all the values, we'll stop here, return to the next power level, or else we will be updating the positions to ensure the optimal power controlling coefficients. So these are the gray wolf total strategy is all about. Searching process, how it is a non-ordered based algorithm. It can go in any direction. It can go in any direction and search a spray and get the optimized locations. So this is what the alpha, beta, gamma algorithms, gray wolf for position vector based algorithm. Cost function is being defined over, and same optimizations have been happened. These were the solutions what we got from the simulation, which was practically connected. And we can see the total harmonic distortion using this gray wolf enhanced gray wolf algorithm was 2.20%. Definitely, it is within permissible limits. So if we compare to model predictive control, which was having 26 percentage, again compared to ANN and genetic algorithm, which was having 18 percentage of TSD, again when compared to previous fuzzy neuro and other one, this TSD value is reduced, and it's into permissible limits. And if we see the discussion, you can see like all the methods: MPC, ANNG, artificial neural networks, genetic algorithm, ANFIS, CRPSO, and EC, enhanced gray wolf algorithm, optimization techniques. We can see that resistance line and reactance values are also reduced. Uh, Current harmonics of fifth and seventh level, which with respect to nonlinear loads, we can see we were able to detect the peak values in 1, 3, 5, 7, 9, 11, in all the ABC levels. And total harmonic distortion, we can see that from MPC 26% to enhanced gray wolf algorithm, we have come down to 2.20%. Definitely one of the best till date. And settling time, definitely any algorithm we apply in this electrical system, settling time is very, very important to avoid the economic losses. We have seen that in the initial model predictive control, settling time was 0.5 to 0.6 seconds, whereas in this enhanced gray wolf algorithm optimization technique, it came to 0.1 second. And voltage swag and swell levels were also reduced. Power factor is also, you can see, usually unity power factor practically is not possible. So we are making sure whatever the best on load from MPC algorithm, it was 0.7 only power factor. In our latest gray wolf algorithm, which is AI based also, it came to 0.98. And we were able to have the economic losses into consideration. Number of switches, initially 12 switches were used. Next, from 2 bridges were used. Now here 2 bridges were only used, minimizing the switching losses and delay time as well, and enhancing the TSD values. So, in simple conclusion, I would like to say that whatever we have discussed about this establishment of the smart grid system of the in individual microgrids, we need to ensure the ECDRs and the smart impedance are designed in the most optimized way. Initially, ANN technique was used along with GA, which was producing 18.32 TSD. Again, ANFIS technique with CRPSO was used, which was producing 6.53 TSD value. We came with enhanced gray wolf algorithm, which reduces the cost of 2 different controllers to 1 different controller technique. And TSD value was very much impressive with 2.20%. And settling time also, fast settling time also, which was initially 0.5 to 6 seconds, came down to 0.1 seconds. And we were able to address most of the power quality issues. And this complete performance of these algorithms were evaluated with IEEE microgrid system in the simulations to the MATLAB. And practically, as said, it is being implemented at Chennai, one of the microgrid stations, smart grid stations, in one of the universities, and I am part of that. And FutureScope, definitely, we have different microgrids together. This was all about only one microgrid connection. We can include multiple microgrids together and can carry out this complete experiment as well. And definitely,
మంగళవారం ఆ రోజు అష్టమి కూడా కరెక్ట్ ఆ రోజు చేసి మనం
and
ఓకే
renewable sources we have been using, like coming up with the rooftop photovoltaic cells, that is solar energy based cells, electric vehicles, biogas, all this coming into picture. Definitely we can focus more and more on this research area to improve the power quality issues and to ensure that the best power quality is being produced to the clients. Thank you, that's it from my side. I am open for any questions. Thank you, everyone. I'm open to the questions. Hope I was able to make a certain impact based on this research topic.
Thank you very much, sir, for your excellent lecture on this topic. That is the design of cost-effective control strategies for high-quality power to AC microgrids. So this is a very, very important one, sir. Nowadays, energy consumption is there, and in that one, we have to follow many cost-effective controls. And you know that every country's development is depending upon the energy consumption and also conservation. And for them, the cost-effective control strategies are very important. And in detail, you have explained them. I hope that this is very useful for all of us. Thank you very much for your interesting lecture, sir.
Thank you, sir. And I'm open to just announce that still this research work is going on, sir, and we have a lot of scope for improvement. Any of the students or any of the faculty members interested to get involved in this or get any practical knowledge on this, I'm open for them as well, sir. Can connect me at any time.
Okay, sir, sure, sir. So now, Atturi Venkateswara Gari's son, Atluri Subbarao Garu, is also present here. Now I request him to say a few words on this occasion.
Thank you very much, sir. I thank Venkateswara Garu, Chairman, Telangana State of Engineers Association, and I thank all the office bearers and concerned people who have worked for this evening endowment lecture. I also personally thank the Mamdala Vijay Karthik for giving excellent lecture and appreciate. And next year, I think we'll have a live program. We thank you very much for holding the conference today. Thank you, sir.
Thank you very much, sir, Atturi Subbarao Garu, for your nice words about on this occasion. Now I request Engineer D. Rama to propose vote of thanks.
Professor Dr. Muhammad Moinuddin Garu, FIE committee member, Engineer T. Venkatesham Garu, past Joint Hand Secretary, Engineer Sheikh Shafi, MI corporate member, past presidents, council members of IEI, past chairman, past honorary secretaries, members of Telangana State Center, corporate members of IEI, distinguished guests, family members of Atluri Venkateswara Garu, his son Subbarao Garu, representatives of media, ladies and gentlemen. On behalf of the Telangana State Center of IEI and on my own behalf, I convey our sincere and profound thanks to the Dr. Mamidala Vijay Karthik, Associate Professor, some Training and Placements Officer, CMR Engineering College, delivered the lecture on design of cost-effective control strategies for high-quality power to AC microgrids. I also thank the dignitaries, past presidents, past vice presidents, council members of IEI, past chairman, past honorary secretaries, members of Telangana State Center, committee members of IEI, corporate members of IEI, and others who have made it convenient to attend the event. I also thank the representatives of media. Thanks one and all. Now I request all to raise for national anthem.
जनगणमन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे, तव शुभ आशीष मांगे, गाहे तव जय गाथा। जन गण मंगलदायक जय हे भारत भाग्य विधाता। जय हे जय हे जय हे जय 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 हे
जय हिंद।
Rama madam, Brahman Sadino, congrats. Vote of thanks, Baji Pino.
Right, sir.
Hello, sir. Good day. Remani Gautam.
Right, sir. Right. Thank you.
Vijay Kartikaru. Good presentation. Congrats.
Thank you, sir. Thanks a lot.
Very happy to talk to you.
It was my
What's up?
pleasure, sir, in front of
Very
all
happy.
the legends
Advance Dasara
presented.
to you. Thank you. Thank you.
Thank you, sir.
मोहन साहब कहाँ है?